Previously, we have seen the typical capacity of MIMO channel, which is given by C is equal to max log 2 maximization of mutual information, which is given by log 2 determinant IMR plus ES by MT and nod H RSS covariance matrix of the source, and then we have H Hermitian. And subject to the constraints on trace of RSS is equal to MT. And then we said there are two cases that we need to study. The first case is when there is no CSI at the transmitter. That means the channel is unknown at the transmitter. And the second case is when there is CSI available at the transmitter. And for the first case, we have said that capacity can be given as summation I is equal to 1 to R, where R is the rank, log 2 1 plus ES lambda I by MT and naught. And this MIMO gives you R parallel CSO links. For example, this is the transmitter and then we have receiver. So in between the transmitter and receiver, we will have R parallel links, where each link has gain lambda I, has the transmit power ES by MT, and each link has noise N naught. And there is a linear increase in capacity. And then we also considered the case what property of H would lead to maximum capacity, and there we said H needs to be orthogonal matrix. Orthogonal matrix, and only then lambda I would be equal to lambda J would be equal to PT by M. That means the power assigned to all the links would be equal. As a result, the capacity expression becomes M times the capacity of CSO channel, and then we can write this capacity expression as C is equal to M log 2 1 plus ES by N naught. And the meaning of orthogonality says that signal transmitting at any one of the channel are not having any influence on any other received channel. So now let us go back to case 2, capacity of channel known at the transmitter. So here what we are saying that if we have a transmitter, we have a receiver. At the this is a channel H in between. Okay, let me first erase it. Okay, between transmitter and receiver, transmitter has multiple antennas, receiver has multiple antennas, and we have a channel matrix H. Now at the receiver, we estimate the channel H, and this estimate should be perfect. And then from the receiver side, we have a feedback coming to the transmitter. Now the channel state information is available at the transmitter, which is known as CSI. And this feedback is also assumed to be ideal feedback, perfect and error free. Here we say full channel knowledge is available, so we have perfect CSIT. H is rank R, 0 mean circularly symmetric complex Gaussian, and the received signal is given by Y is equal to H S tilde plus N, where S tilde is V into S, where V is some recording. So what we can say that at the transmitter side we have some precoding V, and input to the precoding is S1, S2 and so on up to SR, and after precoding we are transmitting the signal into the air. So we have S1, S2 and so on up to SMT, because we have empty number of antenna elements at the transmitter. So we have S tilde would be of dimension MT cross 1, V would be of dimension MT cross R, and S is of dimension R cross 1. So this is multiplication is possible, and S tilde is MT cross 1. So this is some precoding applied at the transmitter side when we have CSIT. Now we know H can be decomposed using singular value decomposition. H can be decomposed into U, D, V Hermitian, where U and V, they are the unitary matrix, and D is the diagonal matrix comprising the singular values of H. So we can expand this expression and we will get U D V Hermitian, and then we have Vs because S tilde can be represented as Vs. So we get this particular form. Now V, what is V Hermitian V? This is identity. So you get U D I S plus N. So now at the receiver side, we can multiply the received signal with U Hermitian. So when we multiply this, we get U Hermitian U, which is again identity, and we get U Hermitian noise, which is another noise represented by N tilde. And you get the final expression as Y tilde is equal to D into S plus N tilde. Okay, so if you expand this, you will get Yi is equal to root Es by Mt sigma I, because diagonal element comprises of the singular values, and then S is the symbol, and this is N tilde. Okay, or we can also understand this by like this. We have Y tilde, which is equal to, let's say, D matrix, sigma 1 up to sigma R, and then it is a multiplication with signal. So you have S1 to SR, and plus you have noise N1 tilde, and so on up to NR tilde. So when you multiply this, what you will get? You will get sigma 1 S1. So you get Y1 is equal to root Es by Mt sigma 1 S1 plus N1 tilde. Similarly, you will get Y2 is equal to root Es by Mt sigma 2 S2 plus N2 tilde. So because of pre-processing that we have applied V, what we are looking at here is that we are not going to get any other term S2 or else. For example, if we are receiving Y1, we will only receive S1. We do not have any influence of S2 or so on. Okay, so H can be decomposed into R parallel seesaw channels. That means we have parallel transmissions. And we also know that singular values, eigenvalues, they are related to each other by this particular fashion. So we can simply replace sigma I with eigenvalues. We get lambda, square root of lambda I here. And we have this particular received signal expression at the receiver. Then the capacity is written as C is equal to summation I goes from 1 to R log 2 1 plus Es by Mt n naught times lambda I gamma I. R is the rank, gamma I is the power allocated to each of the symbol, or it is expectation of mod Si square. Lambda I is the eigenvalues corresponding to H Hermitian, and we have obtained this from singular values corresponding to H, and Es by Mt n naught, okay. So now if you compare this expression with no CSI available at the transmitter, so what is the difference? The only difference is that we have the additional multiplication of gamma I in this particular expression, and this gamma I indicates that we have given power to each of the transmit symbol, and so we have to write the constraint then. Summation I is equal to 1 to R, gamma I is equal to Mt. So as such, this Mt would get cancelled, and we will remaining Es as the total power. Okay, so when channel knowledge is available, we can give different power to the transmitted symbols. So now we want to maximize this expression. So we have this capacity expression. We want to see how we can maximize this expression. So then the capacity maximization problem is given as C is equal to maximization over the constraint. We have the constraint, power constraint, summation I is equal to 1 to R, gamma I is equal to MT, and then we have this expression which we have defined earlier. And for a given set of lambda i's, we can see that gamma I is concave. Gamma I is concave. This objective is concave in gamma I. And if we solve this expression, we will find out that gamma I opt is equal to mu minus mt n naught divided by es lambda I. And then we have plus here. Mu is some constant, and this plus basically indicates that if x is greater than 0, then you have to allocate power, and if it is less than 0, then you do not have to allocate the power. This is a water filling solution. So gamma I is equal to expectation of mod Si square is the ratio of the power on the ith symbol compared to other. And from the previous solution, we have seen gamma I opt is written as mu minus mt and not by es lambda I plus. So plus basically simply means that if x is greater than equal to 0, it is equal to x, and if x is less than 0, then it is equal to 0. Okay, so you can write this as gamma I opt is equal to mu minus 1 divided by es by mt and nod lambda I. And lambda i's, they are the eigenvalues, so they are arranged in a decreasing order. So if lambda 1 is higher, so that means this value will be smaller, and so we have lower levels corresponding to 1 ith mode, first mode, and this mu is the constant line. So as you decrease the value of lambda, let's say lambda 2, this value will increase and the level will change to somewhere here, and so on. We have this, and we have R modes because R is the rank of the matrix. So whichever lambda has higher value, you are giving more power to that stream. So here just look at it, you are giving more power to that stream. This has higher lambda 1, this value is lower, so levels is lower, and you are putting more and more power to this particular case. And as the lambda decreases, this level is shifted above, and the power is now less. And this particular shows that the amount of power that would be associated to the ith mode of transmission. And this solution is water filling solution, and this is applied when the CSI is available at the transmitter site. Okay, let us summarize what we have studied. We have seen capacity is M times C, so we can write capacity as M log 2 1 plus Es by N naught. Then we have parallel stream transmission, so that means we have it can be illustrated in this particular form. We have symbol S1 and so on, symbol SR. Every symbol is allocated some power, let's say gamma 1, let's say there is some symbol S3, you have gamma 3, and this is gamma R. Then we have eigenvalues corresponding to it, lambda 3, the root of lambda R. Then noise is getting added, N1, N3, and then we have NR, and we have the received signal Y1, Y3, and YR. So we have parallel stream transmission. No other symbol is influencing a current symbol. And then we have seen two cases when CSI is not available at the transmitter. So you have equal power transmission. In that case, RSS is equal to IM. And when CSI is available at the transmitter, so we can employ S tilde is equal to Vs. We can employ some precoding at the transmitter, and then S tilde would be equal to V times S, and we can write RSS opt to be equal to V RSS opt V addition, and where RSS opt is equal to the power allocated to each symbol. That means it is a matrix given as expectation of mod S1 square, then we have expectation of mod S2 square, and so on. And what is this value? This value is equal to gamma 1 opt. Gamma 1 opt power allocated to first symbol. And then you have expectation of mod S2 square, which is gamma 2 opt, and so on. You have gamma R opt. So higher lambda I, you give more gamma